Hey guys, I'm doing my presentation on formalizing and equating music through statistics and probability. Recently I've been listening to a ton of music and I realized a lot of the music uses some fundamental patterns and similar structures, which got me thinking if there was a way to study these patterns and generalize, with the end goal to make a function that can auto-generate a musical piece. So obviously this is a very open-ended goal, and at the start it seemed nearly impossible. You may remember ages ago we watched a problem-solving lecture by the mathematician George Polya, who set out a standard guide of sorts he'd made to solve problems. His 4 problem-solving principles were to 1. Understand the problem, 2. Devise a plan, 3. Carry out the plan, and 4. Look back. So first I needed to understand this brief I'd set myself. I wanted to make a function using code that could auto-generate unique music. I decided to restrict my output to only music of a particular genre known as lo-fi hip-hop, due to the fact there are large amounts of data pieces or songs in that genre. Secondly, lo-fi hip-hop has lots of patterns and similarities between songs, so it's very easy to formalize and code. So now I've somewhat understood my brief, I need to come up with a plan. First I zoomed in on what makes up a lo-fi song. By listening to a range of data points, I established the 5 main parts of basically all lo-fi songs. 1. Its chord progression and / scale. 2. The instruments used. 3. The instrument parts. 4. The rhythm. 5. The piece's structure. I now zoomed in further onto each part. First I looked at the musical scale. A scale is a graduated sequence of notes that usually form an octave. It's so important in the structure of a piece as it gives a set of notes that harmonize and sound well together that can be used later to make instrument parts and chords. The reason why notes in a scale relate to each other is actually fascinating. Take these 2 chords for example. Which one sounds better? In the first chord, the 2 notes I played were a C and G. The second note has a frequency of roughly 1.5 or 3/2 times the first one. On the other hand, the second 2 notes were C and F sharp. The second note in this chord had a frequency of roughly 45/32 times the first one. Our brain finds pleasure in stuff it can comprehend easily, so the frequency of waves with the simplest ratios are the notes we find most satisfying and which create harmony. So we now have a way to measure how well notes harmonize together based on their frequency intervals. On the board you can see a major diatonic scale frequency interval chart. All the fractions are relatively small, meaning they will harmonize. Quick disclaimer, pianos are actually tuned ever so slightly wrong. However, as we're conditioned to accept to enjoy the tuning of the piano, we will treat it if it is correct. So now we understand why notes and scales harmonize. Let's try generalize. On the piano, the difference between each note is known as a semitone. If we converted each note on the piano to a number, as seen on the board, we can write each scale as a set, or even plot the scale on a graph. On the board, you can see some different scales plotted. What pattern do you notice? Yeah, exactly. The graph is being transformed on the y direction. Thus, we can make a general formula for creating a scale. Giving the starting number n as an input, the output will be the identity scale set mapped to n. You can see the final formula on the board. Now we can use a random variable which is uniformly distributed with n equals 37 to generate a random value of n over 3 octaves. We can now generate all major scales. I then moved on to generating a chord progression. Chords related to each other in a similar way to notes, with dependence on how rational the difference between the 2 chords' frequency is. Someone had already made a chart of how all chords related to each other in a given scale, as seen on the board. This chart was extremely helpful and included around 95% of chord progressions in every song. As you can see, the chart follows a tree structure, so it's very easy to code, where we start at the tonic or root of the scale, and then randomly pick a node that works accordingly to the chart. We continue this process till we have our full chord progression. I also distributed the probability of picking different nodes based on the actual distribution of chord progressions in songs. i.e., my code is more likely to go from the root to the fifth, rather than a second, as hardly any pieces of music actually use a second, even though technically they're harmonized. The output to this function is a set of sets, with each element representing a note and each set representing a chord. For example, this output could be played on the piano to sound like this. Now I have a way of generating chord progressions. I moved on to my next issue, instrument parts. After listening to more music, I split instrument parts into 5 main types: the chord part, the bass line, the drums, that's percussion part, the lead solo part, and the backing / atmosphere part. I'd already pretty much coded the chord part player using the function on the last slide, so that was finished. I next moved on to coding a bass line, which was quite easy as the notes mostly mimicked the root of the chord progression. For example, next I added drums. This was quite an interesting challenge, and what I did is split each bar into 16 random variables, where different parts of the drum had a probability to play. I again modeled my probability weights and statistical data from music. For example, I realized most songs have a bass drum on beat 1 and a snare drum on beat 2, so the probability weights in part 1 and 5 are altered accordingly. Finally, I had to code the lead and backing instrument parts. As I knew what scale the song was in, I could use a random variable to pick notes from the chord progression output set. By analysing even more lo-fi, I realised lead parts normally had a much more complex rhythm with more notes, while backing parts were normally contained longer sustained notes. It was much trickier to make instrument parts compared to drum parts, due to the fact that in instrument parts the length of the notes vary, while in a drum part the length of the notes are all the same. However, I solved the issue using a random variable distributed from 1 to the maximum length I wanted to beat. If the random variable was measured larger than 1, the code would skip through the subsequent packets in the 16 loop until the amount of packets equal to the random variable had passed. This allowed me to add notes of different lengths. The only difference between the lead and backing instrument parts were the random variables. For the lead part was uniformly distributed from 1 to 4, meaning shorter length notes, while the random variable for the backing part was distributed from 4 to 8. Thus, the notes of the backing track would have on average been much longer. I had now finished 2 more of my fundamental parts of making a song, and the instruments used was also extremely easy. I made a spreadsheet of the different instruments used in lo-fi and how frequently they were used in which different part. This helped me create 4 random variables for each type of instrument part. The random variables were all distributed according to the result from my spreadsheet. E.g., electric piano is used as my chord progression instrument in 50% of all my songs. The only step of the song I had left to create was the structure. Unfortunately, this was by far the most complex step, so I don't have enough time to talk about most of it. The important thing to note is you split a piece of music into different sections, e.g. verse, chorus, bridge, build-up, and depending on these sections, you can randomly select a number of instrument parts to use, and slightly alter the probability weight used in the parts accordingly. After finishing all the logic of the code, I now had to convert this huge set of numbers representing notes and rhythms to something that can be read and played. I spent like 30 hours coding a custom XML compiler that converted my code into something that could be read by a website. So now we've finished going through the process. Let's see the final result. When I press run on my computer, a whole new piece of music will generate, and the chance of ever auto-generating the same piece would be so unlikely. I could sit here and press the button every second for the next 100 years, and I still wouldn't have generated the piece again. Quick disclaimer, obviously this generator isn't perfect, so not all the songs will be good, and as I was the one spotting the patterns, the code will be biased to my own personal tastes. I think more what this shows is a seemingly impossible problem at the beginning can still be broken down into simple mathematical fundamentals, which for me kind of show the beauty and power of maths. So let's listen.